So hello everyone, and welcome to this process webinar. For a bit of context, let me first introduce you to Borasys. So we are a global electrical engineering software and services provider, offering fully customized solutions to help our customers solve their complex electrification challenges in EV. And during today's webinar, we will focus on the inductance analysis of an IPM motor using JMAG. It's my pleasure to introduce you and give a warm welcome to our speaker today. So we have Ganesh, working as a business developer in PW Sim Engineering Solution, a subsidiary of Borasys, and Vinay Kumar, working as application and support engineer for JMAG in PSIM as well. Both of them are live from Bangalore, and they will just start the webinar and the introduction of the company. Lastly, just to inform you that all questions will be answered in the Q&A session at the end of so Ganesh, I think I can give you the ball and start the presentation.
Thank you. Good afternoon, all, and good morning. My name is Ganesh. I'm a business developer, and I will introduce regarding our company. Once. Powersis, our tagline is revolutionize e-design accelerator electrification. Like if you are going with a proper e-design with verification and validate, you can accelerate the electrification process. Like who we are expert in model based design simulation software. We have 30 plus technical electrical engineering from North America, Europe, Asia, and especially focuses in EV industries. And like what we do, our technical experts will help you to avoid the gap in the technology update. This will make the e-motor design robust. Overall, this will be eliminate the production phase risk at this validate during simulation stage. Hence, it will reduce a time to market. Like our focuses, like we have another business unit which deal with EV grid using EMTP software. Till now, we served 20 years, more than 2,500 happy customers over 80 countries. These are our 8 offices located, like 2 offices in San Diego and Detroit in US, 1 in Montreal and Canada. In Europe, we have 3 offices, Axin, and like our headquarters is in Paris and Germany. In India, we located in Bangalore and Chennai. How we reduce time to market? We help in increase simulation volume through faster computation optimization, and we decrease simulation time by parallel processing, and we optimize workflow in such a manner that gives automated and optimized output. And we integrated IT environment, which includes compatibility between GUI, that is graphical user interface, and programming languages. Like we are expert in electrical engineering, which deals with design, electromagnetics, power electronics, and multi-physics simulations. All the above simulations can be carried out with accuracy and we also provide hypercomputing, which provides faster and optimized design outflow. Like Powersys value proposition. Like overall, we are expertise in the simulation tool and provide global service solutions and services. Like our softwares includes a Simba, like it is in power electronics and electromagnetics in JMAG, like which is prime focus of this meeting. And other software in our portfolio includes like Romax in noise and vibration, Actrain, etc. Now our colleague Vinay will continue give the insights about the inductance analysis of the IPM motor. Thank you.
Thank you, Ganesh. So let me share this. Okay. Good morning and good afternoon, all of you. So okay, so today's I am going in this session. I am going to discuss about how we can calculate the inductance analysis of an IPMSM motor using JMAG tool. So in this session, I am going to discuss first for the few minutes regarding what is our tool JMAG, and I will just give brief introduction about our JMAG tool, and later on I will move toward how actually inductance is necessary for the motor performance, and in the next minutes I will be discussing how we can calculate the inductance of the motor with the help of our JMAG tool. So that's all. So JMAG. So JMAG is an electromagnetic calculation simulation device, so which is mainly used for the analysis and simulation of our electromagnetics. So this will be characterized as JMAG Express, JMAG Designer, and JMAG RT. So JMAG Express will be mainly used for rotating machines. So this is entirely a basic model. So which is I can tell like analytical model. And JMAG Designer is mainly used for FEM calculation, so finite element analysis, or we can say finite element method of calculation, so that we can perform using JMAG Designer. And we have JMAG RT, so which is used for control simulation. So we can have the if you are having the control circuit of your module, so with the help of JMAG RT we can deal with the real-time analysis as well. So let me start with JMAG Designer. So JMAG Designer will be having a modelers, CAD interfaces, a pre-post analysis we can do. Solvers will be there, and we can do the parametric analysis and optimization, and we can give the support of scripting as well. And these are the things. So CAD interfaces are mainly we can give the third-party software interface also, like a SolidWorks, CATIA V5, Creo, Pro Engineer, NX, and we can also directly import some of the formats like file formats like .sat, .dxf, Parallel, Step, NX, SolidWorks, like that. And with this we are having some of the modelers. So mainly modelers, what are the modelers we are having here? We can do the 2D 3D modelers analysis, we can do the meshing. So that's why I told for the FEA kind of analysis we are mainly deal with the JMAG Designer. And we have some standard templates, motor templates here to calculate for easy of the analysis for the industry persons. And we have some motor templates, transformer templates, and some of the coiled templates, and we have some inbuilt circuit designer we have. So this will be included with our JMAG Designer only, so you need not to buy from separate. And we have some of the pre-post analysis. What are the pre-post we have means conditions, we can do the condition setting. We have huge amount of material database. So what are the materials that are available in our actual industry or environment, so that database we are having. So if you didn't find your required material database, so you can create your own material with your customized BH curve analysis. And we have good analysis for the measure as well. And we have job schedulers. So once it is done, we can do the post processing, and we can do the report generation, And we have some different analytical tools as well. Where we can calculate the losses, your iron losses or ID current hysteresis losses, or entire system losses we can find. And in today's topic, as I am discussing about inductance, so here we can calculate the inductance in the two ways. So I am going to show you how we can calculate the inductance in the two ways. So one is the method which is having the actual measurement technique, and one more method is there with the help of our tool. A tool is available to calculate inductance. So with the help of tool also we can calculate, and we can do magnetization, field 50 and more. And so compared to solvers, we support SMPs, MPPs, and GPU solvers are there. So for this JMAG will be used, we can use for multi-physics environment also, like thermal, structurals, and magnetic, electromagnetic as well. As I was explaining regarding the parameterization and optimization, which are mainly used for accuracy of your simulation. So in order to get more accuracy, you want to improve your accuracy of the model, so better we can go for optimization. And if you want to find which is the best parameter, so for your analysis, so we can go for parametric analysis also. So we are using a multi-objective generic algorithm for the optimization. And scripting, we are supporting with JavaScript, Python script, and VB script. So yeah, so and what are the applications that we can solve here is, which is completely for magnetic analysis, so electromagnetic analysis, so which are applicable like all the motors, so like IPM, SM, BLDC, stepper motor, axial gap flux motor, and wind full synchronous motor, SRM, SynRM. So all the type of motors we can solve, we can analyze here. And so other than the motors, we have bearing sensors, RFID, spindle motors, and all. So we can do transformer analysis also, relay. And if you are from the switchgear industry, we can calculate electromagnetic relay, electromagnetic braking, clutching as well. And we can also do for solenoids and actuators, heating. So all the electromagnetic analysis background we can perform here. And some of the evaluations that we can perform, so we can perform a cogging analysis throughout NT characteristics, speed, torque, with the help of efficiency map, efficiency analysis, loss analysis, and magnetic flux density. So like this entire package we can evaluate. So this is the capability of JMAG. Okay, so now I will start why actually the inductance is necessary for the motor performance. So when compared to when come for the inductance, we can characterize inductance, entire inductance, as a d-axis inductance and q-axis inductance. So these LD and LQ inductance are we can characterize for two vector control, and which are typically for 90 degrees apart. And that current that flows through the LD, so that is which is through the direct quadrature, direct axis, so which will be mainly used controls the magnetic field. So how much amount of magnetic field need to be generated, and how you can analyze. So everything will be controlled by LD. And similarly, the current that is flows through the LQ, so quadrature inductance, so that will be regarding for the torque production. So if you are having some issues regarding the torque, so a required amount of torque need to generate, or some of the torque is not generating, so if something is mismatching, so we can do. So for both the magnetic field control and torque production control, so we need LD and LQ. Yeah, so let me start with the first one, that is calculation tool. So this directly we have the one tool for calculation of the inductance in our JMAG, so that I will show later how we can do. So with the help of that inductance tool, we can calculate. So normally what happens in our IPM motor, we are using both magnetic torque and reluctance torque. So these are mainly appropriately used for in order to choose the current phase. So in order to improve the efficiency, so some of the broader spectrum, so we need to analyze the inductance. And some of the strong rare earth material magnets are used, so in order to increase the output density of our motor. So what are the main influences? So the magnetic circuit and saturation. So this magnetic circuit saturation needs to be carried out so that in order to evaluate this motor EPM design. And what are the need? So what we need to investigate here is the inductance characteristics. So this will be inductance characteristics. So in order to perform the advanced projection, so we need to go with geometry or the materials non-linearity, or if it is there with respect to the current phase. So this analysis is based upon the magnetic circuit method, so we can say. And so in order to perform the advanced projection of IPM motor design, so we need to go with the FEM. Okay, so in this case, so we can get how to obtain the current phase angle characteristics of a D axis and Q axis, so which are mainly accounts for the magnetic saturation as well as flux linkage in the IPM motor. So it is possible, yes, so to output the torque even in the phases, so where the orientation of the rotor magnetic pole is not orthogonal. Yes, even though if it is our orientation is not orthogonal, so to the rotating magnetic field, so we need to find the rotates magnet pole there. So whenever at this condition, the torque is created with the help of the magnetic resonance saliency. So because of this magnetic resonance saliency, we are getting one torque. So the torque, we can call it as reluctance torque. So this reluctance torque is mainly the source for the stepper motors, or else the switched reluctance motors. So a field weakening control is the exact of restraining these things, and some of the induced voltages that we can get by running the current through the coil, so in order to weaken the magnetic field which is developed by the magnet. So now it is possible because of this induced voltage and with the high rotation, so carrying out this field weakening control will be decreases, so with respect to the torque as decreases at the same time. So what we are doing here is, so we can recover this torque by reducing the weakening of the field. Yeah, so by if you don't want to lose any torque, so we can do the recovery of the torque by reducing the field we can control with respect to the reluctance. So how we can achieve that? So that we can achieve with respect to by increasing in output. So, and finally, the magnetic flux flowing inside the rotor is becomes a very key role here. So in order to reproduce this, so we are doing a magnetic circuit. So we are having the magnetic circuit, the parts, so which are mainly with inductance analysis model and materials non-linearity magnetic properties. So these two need to be very taken care. And for this analysis, I have taken one example. So I have considered a 4-pole IPM SM motor with 24 slots and some stator OD and rotor OD, and which is the gap length is having around 0.5. So the between the stator and the rotor. And I have considered the 35 number of turns per slot, and with respect the phase resistance is 0.814, so which is having star connection. And some of the circuits values regarding the circuit, I am using FEM coil turns and with the UWV. And I am considering some of the settings for our motor calculation tool. So where I am considering the maximum and minimum current is a 5 ampere, and I am going to rotate my motor with some 10 degrees to 80 degrees with in order to find what is the maximum or possible inductance that we can obtain. So for that, I am doing the parametric cases here. So I am just comparing. So how actually inductance is varying from current phases of from 10 degrees to 80 degrees. So how we are performing. So what algorithm that it will taking place inside the JMAG is. So whenever the current is flowing through the coil, so through the rotor turns, so at that time magnetic flux will be created around that rotor. So this density will be distributed at each time, each part, so with respect to the time variations. So from one point of time to another point of time, the current is goes on varies. So at that time the torque will be generated. So once the torque is generated, we can push that to our inductance model analysis. So there we are creating our inductance model. So we are running the inductance analysis, and we are confirming the results. So this is the view or GUI of our JMAG. So the left side is our project manager and right side is our toolbox. And this is the IPM motor. So if your model is a symmetry, we can go with the partial model. Or if our model is don't have the symmetry, you need to consider the full model. So yeah, so this is what I in the starting slides I was explained regarding the designer models. So these are the models that we are having. So we can assign the materials. So yeah, in the right side toolbox, we have the material section, condition section, and you can select the material section. So you can just drag and drop your materials, which is available in our database. So for each part, stator coils, rotor core, magnet, and all. And once it is done, we can give the conditions also. So you can give the current condition, motion condition, and the force condition, torque condition. And so here you can see the motor inductance calculation. So today in this first part of my presentation session, I am explaining regarding how we can calculate this inductance with respect to this tool. So you just drag your motor inductance calculation and drop onto the motor. So you will get this window. So in this window, you need to assign your current direction. So current, you need to go for amplitude with respect to phase, or if you are having the direct axis and quadrature axis values, you can select that. And connection is same with respect to star or delta. So you need to assign the current frequency, number of poles of your motor, 4 poles, 8 poles, like that. And here, as I shown you later already, that I have considered the 5 ampere. So based upon your motor drive, so your drive condition, you need to select. So line current amplitude, and similarly current phase. You can select either line current amplitude or current phase. So once it is done, so you are created now. So once it is done, how it will flows now. So you are created the line to line inductance model. So you are running now. So once you are run, the calculation is done. So here I am considering the rotor position changes from one angle to another angle. So it will take here. And so if you are not interested to give the rotor position change, that is fine. So you will get only one set of inductance values. So you will get the D axis and Q axis inductance calculation. So previously you will be having your models, so you can confirm that. So you can run the motor inductance tool and you can confirm the inductance. So this is one set of calculation. This is another set of calculation. You can compare the both. And this is how the meshing and electromagnetic flux are generated for these conditions. You can see that why meshing is necessary. And based on it, this is a FEA kind of analysis. So each and every part of your motor need to be fine tuned. If it is not fine tuned, there again you can see the error in the accuracy. So some of our customers are interested to improve the accuracy of your model. So at that time, we can suggest them that we need to improve the element sizing. So that's the thing. And this is with respect to the meshing and how our inductance is affecting to our magnetic flux. So as I was discussing LD and LQ, so LD will be with respect to mainly with respect to the magnetic flux creation, and LQ with respect to our torque generation. So we can observe by running the magnetic flux density, how actually the magnetic flux is flowing at particular areas. And for this analysis, we are using some of the set of equations. So from this set of equations, we need to find the reluctance torque and magnetic torque. So this total torque is the combination of reluctance torque and magnetic torque. So reluctance torque can be calculated with if you are having the number of poles, and LD, LQ, and ID, IQ. So that we will get this LD, LQ, and ID, IQ values by running this inductance analysis tool. So I will show in the next slide how the results we can get. So we can use this and set of equations, and we can find the reluctance torque and magnetic torque. So again, this is the advantage here with the help of inductance tool. We are not only determining the inductance and inductance of direct and quadrature axis. Here we are also getting the current values at current phases at each direct and quadrature, and also we can find the torque, the magnetic torque and reluctance torque. So once you are run the analysis, so you are we can visualize the results with so these results you can easily export with respect to the CSV formats, and you can response this data as well. So you will get this I have taken for only one case study, and you will get the current phases at different phases. As I was telling, I ran this analysis for 10 degrees to 80 degrees. So these are the phases, and I got for ID, IQ, LD, LQ, and phi, that flux that generated at each stages. So I can use these values and I can substitute here. So I can easily get the torques. So this is how I drawn here the inductance versus current phase. So here you can observe the d-axis inductance is smaller. So because of the magnetic flux penetrates through the lower permeability of the magnet. So whenever this magnet's flux is passing through the lower permeability, so that's why at that time we will get the lower values in the d-axis, and it is less affected by the magnetic saturation. Because why? Because the large magnet resistance. So in the d-axis we will be having large magnet resistance because of the low permeability. And similarly, you can observe on the q-axis, so inductance, that is LQ in the orange line. So it is has some higher values. Why? Because it will be high because compared to d-axis because of the larger permeability. So the magnet will be having lower permeability towards d-axis, and the magnet will be having larger permeability towards q-axis. So this will affect the magnetic saturation, and because of the smaller magnetic resistance. So here the permeability of the magnet resistance, saturation of the magnetic resistance, these two are plays important role for the inductance at the LD and LQ. So with the help of the results that I obtained, so this graph I had drawn. So this is one set of calculation, and similarly I had drawn by applying the same values to our torques. So you can observe here, so with respect to the current phase angle, and this reluctant torque and the magnetic torque which can be easily calculated by the inductance here, and with respect to the current, and also interlinkage magnetic flux, so that is phi. So with the help of phi, LD, LQ, and ID, IQ, we can easily calculate the torque, the magnetic torque and reluctance torque. Yeah, so this is all about the first method of calculation of the inductance. So next method is with the help of actual measurement. So how we are doing with respect to the actual measurement. So here we are just evaluating the inductance characteristics along the d-axis and q-axis. So when the motor is at saliency, so when the motor rotor is at saliency, we are just calculating the d-axis and q-axis inductance values. So it is possible to calculate the inductance in the d-axis and q-axis just by measuring the no load magnetic flux. Here we are considering as a no load. So in the previous condition, in the previous case, I have considered with load. So here I am considering without load, because what happens here, if it is under loaded condition, or I can say if the motor is operating condition, so there we need to place the LCR meter, so between the two phases. So that's why, so when the rotor is at stationary state, so based upon the current conditions, so if we are having the different conditions like 3-phase, 2-phase, so when the motor is at different running conditions, so there we will get to different drives, so which will be strongly affect our magnetic saturation. So because of this reason, here we are considered for saliency of the rotor condition. So by based upon the changing the rotor stationary position, that is the motor is not rotating, the rotor is not rotating, so just we are changing the rotor position by manually. So by changing this manually, we are calculating the inductance here. And so once the torque is generated, so it is possible to produce the torque even when the phases where the rotor magnet pole and the rotor magnetic field are not bisect. So this is what I meant by saliency, the stationary part, stationary position. So where there is no interlinkage between the rotor magnet pole and rotor magnetic field. So in this case, the torque is created by the magnetic resistance saliency. So that's what I meant reluctance torque. Here, reluctance torque is generated by magnet saliency. And so this magnetic flux flowing inside the rotor, so it becomes the key role for all this. So once the motion is complicated because of the rotor geometry and relative positions of the magnetic fields, so the current dependency on the data of the d-axis and q-axis undergone two axes, so which are namely d-axis and q-axis. So by using the actual measurement of the inductance or with the help of tool, so we can easily simulate our result here. So how we are doing, so this is all about the things. So how we are doing, so we are creating the LD-LQ analysis model here by permanent magnet motor inductance tool, so in order to calculate the d-axis and q-axis inductances. And once the line to line inductance analysis model is done, so we are calculating the q-axis inductance from the line to line inductance maximum value. Yeah. So once your inductance model is done, you are run the analysis, you have got the result. So in that, by using the line to line inductance maximum value, you will get the q-axis inductance, that is LQ. And similarly, by the minimum value, minimum value of your graph, so you will get the d-axis. Okay, so we are comparing the both q-axis inductance and d-axis inductances, so with respect to the model. So this is what the flows. So we are analyzing, previously we are using some analysis tool. So here we are using the LD-LQ analysis model itself. So we are running the model, and with respect to the current phases, current between the two phases. So even though motor is not rotating, as I'm telling again, so we are giving the rotor positions here. So by changing the rotor positions, we are giving the phases between the two currents. So by this, we are obtaining the inductance. So how we can do this in our JMAG? So here I am just taking the graphs. So in the project manager, we will have the option called graph. So in the graph, I am taking the circuit model. So circuit current as well as circuit voltage. So here we have the steps for obtaining the target results. So we are created the LQ analysis model, and we are running the things. And once we are getting the values, so inductance is calculated by line to line inductance format. And so here we are using a Fourier transform of the line circuit current and circuit voltage. So once you are right click on the circuit current and circuit voltage, you will be getting this graph. So in the graph, if you just go to the calculation, you will get the Fourier transform of circuit current as well as circuit voltage. So once you are taken that, so you will be having the real part of the voltage, imaginary part of the voltage, real part of the current, imaginary part of the current. So with these values, so we need to calculate the inductance. So this total inductance, that is line to line inductance, I can tell. So this line to line inductance can be obtained with respect to using this formula that we are used in our JMAG to calculate the line to line inductance value. So we are using imaginary part of the voltage, real part of the current, and subtracting with respect to real part of voltage and imaginary part of the current. And here we are using IR real part of the square of the current and imaginary part of the square of the current. So once you are did this and drawn the curve, so that we can use in our any tool, namely Excel. So there, if you are drawn, so you will get this LA value. So this LA value I have derived by using this formula only. So these are the different phases that I have taken. So from zero rotor position, as I was mentioned, we are manually taken. So this from 0 position to 90-degree position. So when we are manually rotated, so these are the values that we are derived. So you can observe here for 0 position 0.3, so it is goes on. So as I already told, we are getting the q-axis inductance with respect to the maximum value. So this is my maximum value of the line-to-line inductance. So this divides with respect, we will get the LQ value, and similarly the d-axis inductance. So that is the lowest value. So this, or we can say minimum value. So with dividing with respect with the two parts with the 2. So for this line-to-line inductance value, I am getting the LD. So I am just compared this LD and LQ again. So I am getting the same result. So that's what in the first step I had shown. In the first case, this you might observe. So this LQ was high and LD was low. So as I was told, for the same reason. So because of this inductance is small in the d-axis because of the low permeability of the magnetic flux. So because of that, it will affect our iron core, magnetic saturation of the iron core. And once it is affected, so magnetic resistance will be high. So magnetic resistance will be give some good contribution here. So that's why. And similarly for the q axis, so we are getting less, so which is passing through the iron core here, and which is having because of the larger permeability compared to d axis. So because of this only, inductance is high in our d axis. So as the current phase also progresses, and when the magnetic flux is weaker, the iron core's magnetic saturation is elevated. So that is the meaning that the q axis inductance is high. And the last part is the magnetic saturation conditions of the iron core are also different when running a 3-phase AC and a line-to-line current. So the q-axis inductance being generally overestimated, and the contribution of this magnetic resistance to the d-axis inductance is large here. So there is not a big gap between the results that I have shown with the two methods. That is one actual measurement method, and last one is our tool method. So thank you.